about the generic chain. So this is highly important in the Gadgetron. There's lots of material, and we design also, I think, some classes that you can really imitate from for designing as a Kspace reconstruction or image processing, and this is quite useful to use the existing classes for your application. Are you ready?
Yes.
Cool. Nice.
So thank you. So today I have two talks. So this talk is about generic chain. The next one is how to call AI models. So I kind of prepare demos linked both. So the AI model will be called in a generic chain guide. So you can see them as one big system. So I will share my slides now. So can you see my slides? Okay, so this talk is about generic chain and do some demo and inline debug. So here is the framework of this talk. So firstly, we need to clarify why we want to do this generic chain. It involves the dimensions in the ISMRD, MRD format, which is very important. Then we introduce the concepts of triggering and on-the-fly recon. So I will explain what is on-the-fly recon, why it's important in practice in imaging. Then we will review some core data structures which introduce and define for the generic chain. And we go through the key gadgets. Then in the interactive sessions. So I got lots of calls last time for how do we do debug and setting up Gadgetron. Last time I demoed in Windows, but this time let's do it in Ubuntu Linux. I will starting from scratch. So until to a point we can interactive debug generic chain. So if we are more interested, then we can go through the code in this way. It's actually could improve the productivity. So let's get started. What's the motivation of this? Gadgetron is very flexible and powerful, but it also needs the real functionalities, the meat for more fitting into the MR imaging task. When we starting this concept, we want to supporting the common recon task, which is common Cartesian, non-Cartesian reconstruction. Another important aspect is to supporting the deployment of Gadgetron. So instead of besides doing Gadgetron as research, we actually went rather far to putting Gadgetron into a real hospital for the clinical imaging. So if we go there, the requirement can change, which means all the recon has to be fast, has to be tested, has to be valid for every time. It will be inconvenient if we have too many code base to supporting the clinical imaging. So generic chain is actually the backbone we use for the practical deployment. We also want to achieve that by building this generic chain, we will implement the default modules for many imaging applications. Those modules will serve as a basis if we want to further improve our overload class to do something different. If there are some special application which standard behavior may not fit. So I have some applications which we do the most for cardiac imaging. So I have 3 cardiac example, but 1 neuro. So one thing different on this application is, let's say one thing common in this application is they are working on some dimensions of MRD data. For example, in the cardiac Cine imaging, we have a readout and the first encoding dimension, E1, channel dimension. And every image is acquired as a face. Then we can have multiple slides to cover the heart. On the lower left, the late enhancement, we have another dimension set, which being used to contain the product density weighted image and the inversion recovery image. Similarly, on the T1 mapping, we may have set and rep. So set may be a different image for different T1 inversion recovery time. And the rep, maybe you can repeat this acquisition several times for example, free breathing T1 mapping. For the 3D case, we have a second encoding dimension often used, always used almost, ROE1, E2 channel slice. For other 3D application, we can have other dimensions. So the key concepts of this MRD data is this multi-dimensional array. The point is it's not convenient or not correct to design a system that we write a Recon chain for every application. If the key data structure is organized in such way, actually the multi-dimensional array is the key. So if we look at MRD key data structures, for example, the encoding counter, we have all the dimensions predefined. E1, E2, average, slice, contrast, phase, repetition, set, and segment, and user-defined fields. So there are conventions, rather conventions for which each dimension means. For example, if we do dynamic imaging related to cardiac or respiratory, then phase may be often used. If we do multi-echo imaging, then contrast is often used. This mapping is also mapped into the reconstructed image. So showing here as image header, which the average slice, contrast, phase, and the repetition set is kept here. And every image could be 3D, which corresponds to ROE1, E2. So this multi-dimensional array concept is carried over through the MR reconstruction. So let's look at data to say what this means. Also, what's important is the acquisition order of this dimension. So which dimension is looped first, acquired first. It's actually important to determine the dynamic behavior because we want to achieve on-the-fly recon. So I go to another computer. So I have a data set, which is this one, a real-time Cine with 2 slices. So I'm opening it with this MRD software. So I want us to look at this index, so slice and phase. If we go with slice, then you can see slice is 0, then we're starting to acquire every phase. So this data is actually rather long. It's acquired about 100. Uh, 101 phase. Then it's starting slice 2. So then it's acquired all the data for the slice 2. So for different applications, this acquisition order could change. For example, maybe T1 mapping, it may be acquire the repetition first, then the set. Also depends on the sequence. Maybe some people will do firstly doing the set, then repetition. So reconstruction should be flexible to handle this variation in the imaging sequence. So this one give an example of this real-time Cine. There's a Cine acquisition. So for this simple setup, it's actually firstly acquire all the data for the first slice across a few heartbeats, then the second slice. if we recon every slice independently, then it will be like an image stack like this. The point here is after we acquire all the data for the slice 0, it's no point to wait for slice 1. But we can start the recon when data is available. So we call this on-the-fly recon concept. This actually is very important in the imaging session. So I have this movie to show us. This is a 10 slice Cine acquisition. So reconstruction every slice take about 2 seconds. So what I'm showing here is you can see the acquisition is going. So we replay this. We can see the acquisition is keep going. Then the reconstruction already starts after the 1 slice is fully acquired. Then second slice, then next slice. So in this way, we can overlap the reconstruction with the image acquisition. What's important is after all the slice is acquired, this reconstruction will only take a few extra seconds. It's done. So for all the image to be reconned. If we don't do this on the fly reconstruction, then for this 10 slice acquisition, it will take 20 seconds. Then it may disturb the image acquisition. This kind of on-the-fly behavior is very popular among the MR technicians. Actually, for all the application we try to develop, we try to utilize on-the-fly recon to the maximum extent. So we review the motivation of this generic chain. Here is the general design of this chain. So firstly, we have triggering scheme to support on-the-fly recon, which means we will monitor that dimension, for example, slice. If all the image data from 1 slice is acquired, it will pack all the data into a bucket, then pass them to the next gauge. The next one in this concept is BucketToBuffer gauge. So this gauge will receive a data bucket, then organize them into a 6-dimension array, which is RO, E1, E2, channel, NS slice. The key concepts here is user can specify what is dimension N, what is dimension S. For example, we can set N to be set and S to be phase, or we can set N to be repetition, S to be contrast. It depends on your application, how to set them. So every bucket will be converted into 1 or more of these data buffers. Then every data buffer will be reckoned down the chain. It will be firstly go through a preparation for the auto calibration lines. So what I mean, for example, if we do interleaved scan, the imaging data is the reference data. In this case, this gauge will properly prep the reference data. You can also define, for example, if we do interleaved scan, we may want to get a full Kspace by average through all the phase. Then this gauge could do all this preparation job. Then it went to the reconstruction. So reconstruction is a gauge which is defined as where user can derive from this gauge for the specific reconstruction algorithm. For example, in this Gadgetron, we have grappa spirit, nonlinear spirit, non-Cartesian recon, several reconstruction. The task of this gauge is to convert the Kspace array into the image array. The image array converted is also follow this RO, E1, E2 channel NS slice concept. Then reconstructed complex image goes through a few other gauges like partial Fourier handling, Kspace filter, field view adjust. Field view adjust means it's possible. It's actually very common that acquired Kspace size is different than the reconstruction size. Maybe protocol require we do 2 times interpolation. Then this sketch will perform all these tasks. So after this field view adjust, all the image is reconstructed and the field view is reconstructed to the protocol specified size. Then it goes through the scaling. After that, the complex image is fully reconned. Then we can adding more image domain processing on this then generic chain. So we basically finish the Kspace recon stage. Then you can go to an image recon stage. So let's look at all these core data structures one by one. So firstly, it's the acquisition bucket. So I put the acquisition bucket here. It's nothing more than a list of Kspace data buffered as the vectors. So acquisition bucket including data and reference. Data is imaging data. Reference is the auto calibration lines. Every imaging data is contained the acquisition header and HOND array. Also, if it's non-Cartesian, it may contain the trajectory. This is nothing more than an unordered buffer of incoming data. So this data structure is used to, let's say, if we want to trigger by slice, then all the data for the first slice will be put into one acquisition bucket, then passed to the next sketch. Then if the second slice coming, then it will be put into another acquisition bucket. The second data structure is Recon data. So Recon data is converted from the acquisition bucket. Every Recon data including several Recon bits, which including the data buffer. So this data buffer is the key data structure here. It's including this 7-dimensional definition we mentioned, NS slice. It's including data, trajectory, density, header, sampling, like sampling limits. In this case, trajectory and density is optional because user may set or not set them, which Recon has to handle. Every acquisition bucket is converted into one or more Recon data, depends on the setting of NS. For example, if we trigger by slice, then every acquisition bucket will including one data for one slice. Then if this slice data including 100 face and 2 sets, then if n is face, s is size, then this dimension will be 102. So this 200 Kspace will be packed into a 7-dimensional array, then passed down the chain. After the Kspace Recon stage, another one is image array. So after Recon, Kspace array, Recon data structure is converted into image array, which has a lot of similarity to the previous data structure. It follows the same 7-dimensional definition. So you may wondering why we have channel here. In most cases, channel is 1. So after Coil combination, we just got 1 channel. So this dimension will be 1. But occasionally, like interactive session, maybe you have a separate channel. The channel could be more than 1 for device. So this dimension is kept here for the maximal flexibility. Then another 2 important one is header and metadata. Header is image header, which Recon has to organize and fill. Note this header is only 3-dimensional, which means every X, Y, Z and channel share 1 header, which makes sense because we would expect different channel of the same image will have different slice image position, all these fields. Then every image could also be associated with the metadata, which is an MRD meta container. which will contain all the information we want this image to have. For example, image comments, processing history, data row. Optionally, this image array could also include the waveform, also a copy of acquisition header. In some case, image domain processing actually needs some acquisition information. So let's look at the key gadgets of this generic chain. The first one is the hello.
Yeah, it's very. Your slide are stuck on my computer on the acquisition. On the slide where you were explaining what is the Recon bit, what is the ISMM lead data buffer. Not sure if it's wanted or not.
Okay, is it updated now?
Not on my computer. Can you confirm, please?
Let's share again. Okay.
Not
So
yet.
Is it working? Still not working.
Not.
I'm on slide 12.
Oh, we haven't got a video from you yet. You might have to just stop for a moment. I think this happened last time, where Zoom just gets bored of screen sharing.
Okay, so maybe I should stop. Is it updated?
We can see you.
Okay.
Yes, we're back.
Okay, so I'm at slide 12.
Yeah.
Okay, so this is acquisition trigger gadget. So what this gadget do is receiving every Kspace readouts. You can see the gadget is defined acquisition header or either waveform. Then depending on the trigger dimension we defined, it will put all the Kspace data into that bucket. In ISMRD acquisition bucket structure, then send to downstream. In the configuration, it's normally configured like this. So we can have a trigger dimension and a sorting dimension. So if we set trigger dimension, for example, to be slice, then every data from one slice will be passed to the next sketch. The sorting dimension is extra. For example, if we acquired several face in one slice, we may set sorting dimension to be face. Then before it's sending, it will sort the data to put phase 0 first, then phase 1, then phase 2. If we don't set any of this, then it will pack all the data into one bucket, then send them over in the close call of the gadget. So this is a gadget which taking the every Kspace readouts, then pack them into a bucket. The next one is a BucketToBuffer gadget. So what this gadget do is take a acquisition bucket, then convert it into one or more this 7-dimensional structure, the Recon data. The key concepts here is the n dimension and the s dimension. So user can specify what is n and s, depends on the application. So this offers the reconstruction a lot of flexibility to looping, to doing the looping of the Kspace. How do you want to organize the Recon task? So why we choose 2 more extra dimension, n and s? So in the first version of this design, we actually had 3 dimensions. You know, this a bit arbitrary. You can have how many dimensions? So MRD can have 10 dimensions. If we have all 10 dimensions here, then it won't do anything for us. if we have two fields, maybe one more dimension, then it's not flexible enough for the reconstruction task. So after review all the use case, we will be able to come out. We found the two extra dimension will fit most needs for the common reconstruction task, which proved to be true after using these generic concepts for quite a while. Other comments is every Recon data, it will separate the imaging data and the reference lines into two 7-dimensional array. It's possible that some dimension of reference is to be 1. For example, if we have 10 sites for the T1 mapping, then it's very likely sequence only acquire 1 site of reference. So in the reference, the site dimension actually is 1. Even in the imaging, it's 7. It means all these 7 sites of Kspace will share 1 site of reference. So Recon has to be able to handle this. This BucketToBuffer also also process the trajectory and the density function if they are available. The next sketch is the reference preparation. So this sketch is a helper sketch. There are so many use cases how we want to organize the auto calibration data. So we come up some common use case for this topic and implement them here. So basically 2 modes we implement. One is average cross NLS, which means let's say we have n dimension to be 10, but we want all these 10 Kspace to share 1 reference data. For example, if we want to do a T2 star mapping, you may want to, definitely we want all the echoes image to share 1 set of graph coefficients. So the influence of reconstruction is minimized. So then in this case, we can set average for all n to be true. Then all the n dimension will be firstly averaged, then reference become 1. Another mode is we can select which one we want to use. For example, maybe you want to use second set for the reference. Then we can set this n for reference to be 1. So input of this sketch is Recon data, output is Recon data. What's changed is the reference array. It will be modified, either averaged or picked, or you can also define filter the reference data, all kinds of handling. It also handles a special case if there are no acceleration. In this case, reference will be empty because it's just no auto calibration data was acquired. Another dimension is starting from this sketch, we have 3 debug parameters. It's debug folder variables and perform timing. So if we set debug folder, all this sketch will try to save the intermediate results as the array into this folder for the debug. If we set variables, it will print out lots of information. And the timing is for the key steps, it will give the timing information. For example, the let's say grab a kernel calibration, how many milliseconds it may take. The next one is Coil compression. So after we prep the reference data, Coil compression, we call it eigenchannel. We will take the reference data, then compute the coefficients. It's optionally, it can also perform the Coil compression, which means we can specify how many channels we want to keep. Or we can specify what's the percentage threshold of energy we want to keep. We want to throw number of modes kept has priority. It may convert 32 channels into 16 channels. The behavior of this sketch is even we don't throw away any gauge in the coil compression, it will still convert the all the channel into eigenchannel. So input output is still a Recon data, but in this case, both data and reference will be changed to the Recon channel. Coil compression coefficients is only computed on the reference data, then applied to the data, to the imaging data array. Then the next one is Recon. So we have generic Recon gauge, which is defined as a parent class. Then we can specify, actually implement every specific reconstruction algorithm. In the Gadgetron, you can find the grappa, and for this course, I added a grappa AI gauge, which is to using PyTorch to run a grappa as a demo. So we will look into it in next talk. It also has a linear spirit, non-linear spirit, non-Cartesian. So the key concepts here is maybe for your imaging application, all the previous modules gauges can be reused, but you have your own algorithm. Then this is the place to implement it. So the parameter of this gauge is subject to every algorithm, reconstruction algorithm. But the key concepts here is this set of gauges will take in the Recon data structure, which is Kspace, well-organized, reference prepared, and maybe converted into eigenchannel. The task of this gauge is to convert Kspace data into this image array. Basically, we'll reconstruct complex image. It's follow the 7-dimensional convention all the way, and I mean, in general, for a reconstruction task, this gauge is the place which will take most of the time. So after we got complex image, there are several optional processing we often need to do. For example, partial Fourier handling. If we do a Cartesian reconstruction, it's very common, at least in Cardic, we do doing partial Fourier. So partial Fourier handling by default is implement two types of handling, which one is pulse, another is filter. This gauge will automatically determine which portion of Kspace should be processed for partial Fourier from the protocol information. The user can specify the parameter subject to the algorithm we use. If we have some other partial Fourier algorithm, then that's the place to implement. So after partial Fourier handling, we can do very common, also in vendor scanner, doing Kspace filter, some type of Kspace filter. So what Gadgetron implement is a separate dimension concepts. So user can specify filter, either same filter or different filter for every dimension. And we take some thoughts for which filter we want to implement. So we, after some analyze, we finally default give user the Gaussian filter, which I want to show this picture here. So just recap why we want to do Kspace filter. If you have object, you have a continuous indefinite Kspace. Then after we do imaging, we cut it. So in the image domain, it's generate all this ringing. We want to get rid of the ringing, but it's a trade-off. So for the remote lobe, it will determine the ringing. For the main lobe waves, it will determine the loss of resolution. So we want a filter which supplies remote lobe sufficiently well, while the main lobe is not got too wide, so we lose too much resolution. So if we compared several, we actually compared many different filters. So as this picture show, on the left, that's frequency response. on the right, that's the image domain response. If we compare this Gaussian filter with sigma 1.5 pixels, that's in color of red. The blue is ideal. So blue is the imaging, basically the the best you can achieve. If we compare it to some vendor supplied filter like this Turkey weak or medium, actually Gaussian is very good balance of the main lobe width and the remote lobe suppression. So for this default filter on the scanner, the main problem is its suppression for the remote lobe is pretty bad. Even its spatial resolution is slightly better. So after many imaging experiments, we decided that's not the ideal. So we put in this Gaussian as the default implementation for Gadgetron. Of course, this is a place, if you have your own filter, that's a place to implement that. Then we come to the final stage of this Kspace Recon. It's including the field of view adjustment and image scaling. So field of view adjustment is to, so in all the previous steps, the reconstructed image is supposed to follow the acquired matrix size. But the protocol may require us to recount the image to a different size. The most common use case is 2-time oversampling. If we have acquired the image size of 128, then after 2-time oversampling, its user may be expected 256. So this sketch will do the Kspace oversampling. In some case, maybe we have a phase encoding oversampling. In this case, you may want to cut back some lines. So this sketch will detect all this information and process image properly. The final stage is the scale. So if we do SNR unit scale, which is the default for the Gadgetron linear reconstruction, in that case, noise is scaled to be 1. So depending on the imaging SNR for the cardiac application, the SNR could be quite low, even lower to like 3 or 5, which means the pixel value, the mean will be like 3 to 5. It's way too low if we convert them to short, which sending back to scanner. So we can supply a scaling factor here. Normally we use 10 or 100. This sketch also allow we do the constant scaling of auto scaling. Constant scaling is we scale image by a fixed value, which in most time we found it's most clear for the use case. For the auto scaling, for example, for the interactive MRI, the image gain could change from the view to view. Then auto scaling may be more applicable. If we do the auto scaling, it has a mode that we can scale only once, which means, let's say we have a multi-echo acquisition. We don't want every echo have different scale factor, right? Otherwise, we can't offline do, for example, T2 star fitting because we don't know the gain of every image. So it will estimate one scale factor, then apply it to all the following image array. Then after this sketch, we got the proper complex image reconstructed from the generic chain. So let's look at one example of this generic chain. I use this grappa RealTime Cine as an example. Firstly, let's focus on this trigger dimension. It's set to slice. So all the data for every slice will be sent over. It can achieve on-the-fly recon. Then we decide what's N and X. We know this application has several multiple image phase, but only one set. So it's no harm to set N, S, and set. This dimension will always be 1. The phase is whatever phase we acquire, which means all the phase will be recounted together. Then it will prep reference. So normally when we do the Cine imaging, we do the TPET interleaved scans. So the standard way to reconstruct this kind of image is to average all the image phase to get one full Kspace as reference line. That's why we set this average cross n to be true for this behavior. Then we can do coil compression. So in this default setup, I don't throw away any channels, but instead all the channel is converted into eigenchannels. Then it's come into the reconstruction batch. What we'll do is take the prepared data and reference, then convert them into image array, then go down the chain. If it has partial Fourier, this chain will handle it. If not, the image will be just passed by without change anything. So this is the concept of generic chain. Let's do some demos on this. So as I said, last time I got lots of comments on how to set up Gadgetron. So I decided to combine them into one session, into one demo here. So we will set up Gadgetron on a Linux computer and go through some gauge of the generic chain. So I switch to another computer. Okay, so this one is a Linux computer I will use to demo today. Firstly, in the Gadgetron wikis, we have this page, how to debug using Eclipse. It's give the step-by-step instruction how to set up. So I will basically follow up these steps. Let's start it by installing all these dependencies, which actually I already installed, but let's see, it will just run and do nothing here. Then for your Ubuntu 20.04, it's better we compile this DCMTK Google test yourself, which is easy to follow comments here, which I already did. Then the meat is this lines. So what this line doing is to try to set up Gadgetron as Eclipse project. Then later I will use Eclipse to demo the inline debug. Then we can set ASMRD repos, Gadgetron repos, then Python repos. So what I did is I copy exactly all these lines into a script here. So I will run this script. What this script will do is it will firstly clean my local installation. So my Gadgetron was installed local folder, home local, and it will. So by default, I put my code into home MR programs. So I will be brave. Let's nuke this folder. Okay, I got nothing here. Then let's run this setup. It will clone all the repos, then set CMake, then compile them. By default, I changed the compilation mode to the debug, so we can see we can do the inline debug. But I will demo how do we, at least how I normally do it, to switch between debug and release, and how you config CMake. So it's compile and installed MRD. Now it's compiling the Gadgetron. It may take 1 minute or two. So in general, in Linux, compilation is very fast. When you do the make, you can give how many jobs, -J, maybe 20 or 30, depending on how many core you have in your computer. Then it will do the parallel compile, so speed up this process. So almost done. So it will finish compile this Gadgetron and install them into my home local folder. So you can say it's do installation. Then it will clone and build the Siemens to SMRD converter. And also install the SMRD Python 2 package, which needed if we want to run the Python Python demo. Actually, we are now using Gadgetron Python. So. Okay, so everything is installed. If I go to my local folder, it's everything is installed here. For example, bin, I have Gadgetron here. So next step of this process is to we need to download and install Eclipse, which you can find the Eclipse here. Then click download. Then you can download this package and install them. So I already downloaded them. So after unzip this package, it's including these contents. Then we can run this Eclipse install command. Then you can choose the path to install the Eclipse. So my Eclipse was installed into so I recommend the latest Eclipse version instead of the one coming with Ubuntu. The one coming with Ubuntu is pretty old. Just one more comment before we proceed. So if we look at this MR program folder, these scripts will clone all the Gadgetron SMRD software, and also will create this build Gadgetron debug release, these folders. If we go to this Gadgetron debug, you can see it's all the CMake produced files. So I normally use the command ccmake from this to look at the command. So in the ccmake, it's basically an interactive user interface for the CMake. You can see what we do. This computer doesn't have CUDA, so it's set to off, and it's using MKL. So if I press C for config, it will config the CMake, then press E to exit this. Then press G to generate the project. Then we can do the make. This one you can do parallel compile. So after we install the Eclipse, what we can do is we can import all this build command. So let me show you. You can go file and import. Because we already create project in Eclipse, so you can say import project, existing project into Workspace. So you can do next. Then let me import this Siemens SMRD. You select this folder, you select open. Then This is because I import yesterday. So let's try to do it again. We can delete existing ones. Okay, so you can import, for example, I import SMRD project, then you can find the source in the source directory. Then we can open them to edit. For example, like all the interactive editors here. So let's continue import Gadgetron. Then you can find all the source code in the source folder, organized as the Gadgetron repos. So what we want to do is we want to walk through some generic chain gauge. So let's go to the gauge, MRI call. Let's open this acquisition trigger gauge. Then we can certainly put a breakpoint. Let's just put a breakpoint in its find. In its process. If you double click here, if you put a dots, that's the breakpoint. Then if you go to this view, you can see we set a breakpoint here. Then let's set another breakpoint into BucketToBuffer. Let's set them also to the process. Okay. Actually, this may not work. Okay, another breakpoint. Then this example we will be using the grandpa gauge. So let's go to grandpa gauge, then set a breakpoint. Okay. Now to debug Gadgetron with this, in this wiki page, it tells us we need to set some pass into the environment variable, normally on Linux in the B shell RC file, which I already did. So the system can find the Gadgetron home library loading path and the Gadgetron command, so which I will not do here. But if you want to follow this wiki page, then you have to set these variables. If we want to go to this project, it's convenient after every time we change the code, this auto compilation could compile and install the project. So you can either click this install project, then do a build. It will just install. Or I normally like to create a target. Let's say call it make install. We build all the projects, then we can change it to install. It will compile all the change. We don't have any change, but it will install. Then we want to debug Gadgetron. So we go into this project, we go to debug as. We can set another debug configuration. which I set. So I want to debug my Gadgetron process. The Gadgetron was installed on the home local folder, so it's setting like so. You can set parameters supplied into this Gadgetron command. So I set them, so we will run on port 9008. Actually, you can optionally setting those environment variable here, but I normally set them in my B shell RC folder. So if you did all this, then we can say debug. So by default, this Eclipse will starting to run your process and switch into this debug perspective. And it will stop at the first line of the main Gadgetron call, and you can press this resume. It will keep going. So you can say Gadgetron is listening to the port 9008, and I have some breakpoint setting here. Now let me send some data to Gadgetron. So I prepared this 2 slides real-time Cine data, which is also uploaded to the exam folder, which is this H file. I will send them through. So I call this client on the port 9008. So I will take this data, sending to this computer, which is Bermuda. This computer has a name. I'm sending to port 9008. I have my debugger listening to Gadgetron at 9008. This one is normally I like to send the image back as analyzed format. Or you can do H5. It's on Windows, so analyze sometimes it's easier for me. So let me do this. You can see the debugger is watching data sending through, and the debugger is watching. Now it's stopped at the first breakpoint in the acquisition trigger gauge. So you can here step into it or step over it. So if you have a function, step into means step into that function. Step over means process that function as a whole. So I will press F6 to step over. Then you can see it's the process is step over to every line. If you put your cursor here, you can check the variables, what they are, what's their values to a limit. So Eclipse can show most naive structures in C++, but for some complicated structure, it may not be able to give you all the information. But in general, it's much better than we only do a print command. So if I press F8, this debug process will continue. So it's trying to process some noise data. Then because it's compiled in debug mode, it's a bit slow. But now we, you see the first bucket here, if we look at the log, it's saying sending first bucket, then it's triggered the first bucket to buffer gauge. This bucket has 2040 lines. If we look at this data, we can check which scanner counter we are. Okay, as we can see, the last line of slash 0 2040. So it's packed all the 2040 lines and set to the bucket to buffer. So that's how you follow and trace what this Recon do if you have a rather dynamic and complicated task. So this BucketToBuffer will convert every bucket to a few Recon data. Then if we let this continue, it will try to go through the Coil compression and prep reference, then come to the graph reconstruction. So we are not at graph reconstruction yet. So as you can see, it stopped at graph reconstruction. Then it's coming back with this Recon data. If we do F6, then if you check what's in this Recon data, we can see it has data and reference. If we look at data, then data has HOND array. If we look at the dimensions, you can see it has a it's not that. 128 by 96. That's ROE1. E2 is 1 because it's 2D acquisition, 20 channels, and n dimension is phase, 102 phase, and one set and one slice because we trigger by slice. So that's how you can monitor every step of this reconstruction. Then if we let it go, it will compute and recount the image. So we recount 102 image. This recon gadget is stopped again because this data has 2 slices, so it will trigger twice. So your recon gadget will be called twice. So let it go further. Then this recon should stop. Everything should finish. Then you can stop your debug. On the client side, we can see all the image is coming back. If we go to this folder, we can see all the imagery we reconstructed. We can open any one here. So it's a Cine image. So that's all I have for this generic chain.